Have you ever imagined what it would be like to travel back in time to witness the dinosaurs or to see the future? This tantalizing idea, a popular theme in science fiction, has captivated our minds for generations. Time travel, in its essence, is a journey through the fourth dimension, a leap across the temporal continuum that shapes our lives. From H.G. Wells' iconic Time Machine to the DeLorean in Back to the Future, these stories have fueled our curiosity and sparked profound questions. What is time? How does it work? And how would our universe respond if we could manipulate it? Time travel is not just a storytelling device, it's a thought experiment that pushes the boundaries of our understanding, forcing us to grapple with the fundamental laws that govern our reality. It's a concept that's as fascinating as it is perplexing, a riddle wrapped in the enigma of our universe's fabric. But is time travel really possible, or is it just a figment of our collective imagination? To answer this, we turn to the world of theoretical physics and the genius of Albert Einstein. Around the turn of the 20th century, Einstein proposed two theories that have profoundly shaped our understanding of the universe: the special and general theories of relativity. The special theory of relativity, published in 1905, posits that the laws of physics are the same for all observers, regardless of their motion or orientation. This theory introduced the idea of space-time, a four-dimensional fabric where events occur. An intriguing consequence of this theory is time dilation. Imagine two clocks, one stationary and one moving at high speed. The moving clock, according to special relativity, ticks slower than the stationary one. This is time dilation. So, theoretically, if you were to travel at near-light speeds, you'd age slower compared to someone stationary on Earth. In essence, you'd be time traveling into the future. Now let's delve into the general theory of relativity, which Einstein published a decade later. This theory describes gravity as the warping of space-time by mass and energy. Imagine a bowling ball placed on a trampoline. The ball would create a dip or a curve, right? That's essentially what planets and stars do to space-time. This theory introduces the tantalizing concept of wormholes. Think of wormholes as tunnels or shortcuts through space-time. If we could find or create a wormhole, we might be able to traverse vast distances in the blink of an eye, or even travel through time. However, wormholes are purely theoretical, and the idea of creating or sustaining one presents numerous challenges. For one, they might require exotic forms of matter with negative energy density, something we've yet to discover. So, according to physics, time travel may not be entirely out of the question, but what would it actually entail? Scene script. Imagine you have a time machine. How would it work? In the realm of theoretical physics, several models for a time machine have been proposed. One of the earliest and most intriguing concepts is the idea of rotating cylinders. Proposed by Frank Tipler, a mathematical physicist, in 1974, the Tipler cylinder suggests a massive, infinitely long cylinder spinning along its longitudinal axis. The rotation creates a frame-dragging effect which, according to the theory of general relativity, could allow for a loop in time to form. However, the feasibility of this model is questionable as it requires the cylinder to be infinitely long, which is not practically possible. A more popular and perhaps more feasible model is the concept of traversable wormholes. These are theoretical passages through space-time, created by warping the fabric of the universe itself. The concept of wormholes stems from the solutions to Einstein's field equations in his theory of general relativity. However, keeping a wormhole open would require a form of negative energy or exotic matter, a concept that is still largely theoretical and unproven. Both models present significant technological challenges. For instance, we currently do not possess the technology to create a rotating cylinder of such immense mass and scale, nor do we know how to create or sustain a wormhole. Even if we could, the potential risks and unknowns are enormous. We still don't fully understand the implications of time travel on the fabric of space-time, or the potential for catastrophic events like the creation of a singularity. Moreover, these models are based on our current understanding of physics, which is still incomplete. There are aspects of the universe we don't yet understand, like dark energy and quantum gravity, which could potentially upend our understanding of time and how to travel through it. Even if time travel is theoretically possible, making it a reality would be an extraordinary feat of engineering. But who knows? Perhaps one day, we might just figure out how to turn the dial back, or even forward, on the clock of the universe. Now let's assume you've built your time machine and you're ready to take a trip to the past. But wait, could you change history? This question brings us to the fascinating world of time paradoxes, where cause and effect can become a twisted maze. One of the most famous paradoxes is the grandfather paradox. Imagine you travel back in time and accidentally prevent your grandparents from meeting. If they never meet, they can't have your parent, and you can't be born. But if you were never born, how could you have traveled back in time in the first place? It's a mind-bender, isn't it? Then there's the bootstrap paradox, named after the saying, pulling yourself up by your bootstraps. This occurs when an object or piece of information sent back in time becomes trapped within an infinite cause-effect loop. Let's say you go back in time and give Shakespeare a copy of Hamlet. In his timeline, he publishes it as his own work. Fast forward to your original timeline where you find the play, take it back and give it to him. So, who really wrote Hamlet? These paradoxes highlight the potential consequences and philosophical implications of changing the past. If we can change the past, it would mean that history is not set in stone, making the future unpredictable and shattering our understanding of causality. It raises questions about free will and destiny. Are we free to shape our own paths? Or are we bound by predetermined outcomes? However, some theories suggest that time might actually be self-correcting, that any changes we make would simply create a new timeline, a parallel reality, leaving our original history intact. This is known as the multiverse theory, which suggests an infinite number of universes, each with its own unique timeline. Time travel might not be as straightforward as it seems in the movies, but then again, reality often isn't. So, while we may dream of hopping into a DeLorean or stepping into a TARDIS, we must grapple with the complex paradoxes that time travel presents. It's a fascinating journey, one that continues to captivate scientists, philosophers, and dreamers alike. Despite the complexities and potential paradoxes, the idea of time travel continues to fascinate us. It's the quintessential question, isn't it? What if we could revisit the past or venture into the future? This allure isn't just about curiosity, but it's also deeply intertwined with our spirit of adventure. Akin to the explorers of old who dared to traverse uncharted waters and scale the highest peaks, we are drawn to the unknown, the unexplored frontiers of time. This fascination also stems from our innate desire to comprehend our place in this vast universe. Time travel, in its essence, is about transcending the constraints of our temporal existence, about reaching beyond the now. It's about challenging the very fabric of reality as we know it, and daring to imagine a world where the linear flow of time is not a boundary, but a path to be navigated. Whether or not we'll ever be able to journey through time remains to be seen, but one thing is for sure, the journey to understand it will always be a fascinating one.